All right, so we're going to carry on with Learning Guide 6. This is actually, it says Lesson 3, but it is Lesson 4, which is related rate problems involving triangles. So if you remember in Lesson 3, we had a question that involved a triangle, and we used similar triangles and that kind of idea. And now whenever you've got a triangle question, it can prove to be maybe a little bit more challenging, I guess, because you just have extra steps. But you want to remember things, obviously, like the similar triangles, that you can use a formula there, a ratio there. And then you also want to remember, obviously, Pythagorean Theorem. So we're going to use both of those in these next few examples. All right, so let's look at the first one. A 6-meter ladder is leaning against a wall, and its foot is sliding away from the wall at a speed of 1 meter per second. Find the rate at which the top of the ladder is falling when the foot of the ladder is 3 meters from the wall. Assume that the wall and the floor are perpendicular. That's handy. So obviously we've got a right angle triangle there. And we know Pythagorean theorem obviously kind of pops into our head when we see that. So remember the step-by-step that we talked about in that last lesson was, number one, draw your diagram and label it as well. Okay, so if let's call this X and this Y. A 6-meter ladder, now this is unchanging. 6 is always going to stay as the 6. Then it's saying that its foot is sliding away from the wall at a speed of 1 meter per second. So that means that this guy is actually getting a little bit longer, and the top of the ladder is falling. So, you know, if we kind of time-lapse this, this is what a later stage of this ladder would look like. Now, let's label things. So obviously we know what our dx over dt is. It does say that it's 1 meter per second. Now, what some of you will be questioning, do I make this a positive 1 or a negative 1? Now, if you remember in that last lesson, I just kind of mentioned briefly that our rate is kind of determined by where we're going from our origin. So if we're going towards the origin, so let's say if this is my origin and my distance is coming this way, that's going to be a negative. And again, because my distance is decreasing. If I'm going away from my origin, that's now going to be a positive. So in this example, if I use that kind of idea, my origin, because it's just talking about the wall, if my ladder is moving away from the wall, if that x is getting bigger, then I know that that's going to be a positive rate. Okay, so that's just kind of one way of remembering it. Think about where your origin is. Now the question is saying, what rate is the top of the ladder falling? So we're looking for dy over dt. And it says when the foot of the ladder is 3 meters from the wall. So we want to say when x is equal to 3. And remember, I mentioned this quite a few times in that last lesson, we only use that after we take the derivative. Okay, so we want to take the derivative first. All right, so we've drawn a diagram, we figured out what's going on. Now we want to figure out a formula that's going to help us solve this. Well, really the only formula that we've got is that a squared plus b squared is equal to c squared. But in this question, we can be a little bit more specific. We can say x squared plus y squared is equal to 6 squared, because again, that 6 is not changing. It's not getting longer or shorter. All right, now with this right now, there's really nothing that we can do. I can't substitute anything in. So we want to just take the derivative of this. So we've got our 2x. Remember, everything is with respect to time. 2y dy over dt is going to be equal to 0. Now at this stage, you guys, this is what started to panic me when I first started to kind of review this, because I hadn't done it since university, which is a long time ago. When I started doing this, I started to panic thinking, oh my gosh, okay, well I've got an x and I've got a y. I have a value for x, but I don't have a value for y. I've got a value for dx dt, and we're solving for dy dt. So what do I do about that x? And then I would start to panic and think, uh-oh, what am I missing here? Did I make a mistake? No, I didn't make a mistake, but what you have to recognize is that there are two variables, and we've got an equation up here and here that will actually allow us to solve for y. Now that I've taken the derivative, this is fair game. So I know that x is equal to 3 is okay, so I can actually use that in this equation. It doesn't matter. So now I'm going to say 3 squared plus y squared is equal to 6 squared. And see how that's awesome, because now we can solve for the missing y. All right, so y squared is going to be equal to 36 minus 9. So y squared is going to be equal to 27. So y is going to be equal to the square root of 27. So now I can plug that into my equation and all my other values. So I've got my x, which we already said was 3, my dx dt, which was given as 1, plus 2, now I know y, is the square root of 27, dy dt is equal to 0. Okay. So now I can simplify. 2 times 3 times 1 is 6. So I'll just move that to the other side. So I've got 2 root 26, or sorry, 2 root 27. dy dt is going to be equal, oops. Oh, yeah, there we go, to negative 6. Again, because we moved that 6 over. And now just solving for dy dt. Negative 6 over 2 root 27. We want to try and simplify that, so that's going to be negative 3 over root 27. And guys, if you remember that 27, we can actually reduce 27. So that's going to be 9 times 3. And so the square root of 9 is 3 root 3. Okay, and then these guys would also cancel. So I would just have negative 1 over root 3 meters per second. Okay? All right. Next one. And again, remember, I think I forgot to mention this in this one. Don't forget, I get boring. So stop, fast forward, and make sure that you guys can do these on your own. All right, example number 2. A spotlight set on the ground is shining on a wall 20 meters away. A person 1.7 meters tall walks away from the light toward the wall at a rate of 1.4 meters per second. At what rate is the shadow cast on the wall decreasing in height when the person is 14 meters away from the light? So this one, there's a lot of information. Certain things are not changing, so that's probably what I would start to label first. A spotlight set on the ground is 20 meters away. So from here to here, we know is going to be 20 meters. That's not changing. A person, 1.7 meters tall, again, not changing. Walks away from the light toward the wall at a rate of 1.4 meters per second. So we're kind of talking about the light as the origin, right? Like they're walking towards the wall from the light. At what rate is the shadow decreasing when he's 14 meters away from the light? So the light is kind of like our origin. So I would probably put a variable here between the origin and the person walking to and from the light. Okay, and what this is saying now is at what rate is the shadow casting on the wall, I'll back up a little bit. A person 1.7 meters tall walks away from the light toward the wall at a rate of 1.4 meters per second. So we know now that dx over dt is going to be 1.4 meters per second. And like I mentioned in that other question, because this person is walking away from the origin, that distance is getting bigger, we know that that rate is going to be a positive rate. All right, and the question is saying, at what rate is the shadow cast on the wall? So this guy here, which has already been labeled y for us, is it decreasing? So we're looking for dy over dt, and that's going to be equal to something. And just as a little note, it kind of makes sense if that's decreasing, the answer should be a negative. So that's one way of just kind of checking to make sure that we're getting it right. And then it's saying, at what rate is it decreasing when the person is 14 meters away from the light? So that's talking about x. So this is when x is equal to 14. Now remember, that we can use after we take our derivative. Now looking at this, guys, you want to think, okay, well, what formula am I going to use? And this is a triangle, so pretty much we're using Pythagorean Theorem, or we're using similar triangles. Well, in this case, Pythagorean Theorem is not really going to help us because we're not looking for that hypotenuse, nor do we have it. So similar triangles is the method that we are going to choose. And similar triangles, remember, is just a ratio. It's quite straightforward as long as you can remember it. And basically you can think like rise over run, anything like that, that's going to help you. But think I've got one big triangle right here, and then we've got one little triangle right here, and they share that origin, which means that we can use the similar triangle. So if I do that, basically rise over run, y over 20 would be the big triangle, and then 1.7 over x would be the little triangle. Now from this, there are actually a couple ways that you could do this question. And what I have found in the past, there's a shorter way of doing it. And in fact, that is taking the derivative as is. So if you take the derivative of this using the quotient rule, so just take the derivative of y over 20, and then the derivative of 1.7 over x, and then solve, it's actually a quicker method than the one that I'm going to show you. And the reason that I'm not going to show you that one is because I've just found in the past that the majority of students right away when they see this want to get rid of their fractions, which is great. I mean, nobody really likes working with fractions anyway. So what I found a lot of students do is they cross multiply. So they do this. Okay, and then they've got a nice linear equation that is fraction-free, and we can take the derivative of it quite nicely. Now, the only problem is that this is kind of added in an extra step, but I wanted to show you how to do that extra step in case you want to choose this method. If you want to, you know, like I say, always pause it, try it on your own, whatever method you want, and then just make sure you can get the final answer the same. So we're going to take this derivative now, and basically this is like our u and our v, right? So I've got my x times dy over dt plus y times dx over dt, and that's going to be equal to 0. And now at this stage, you're going to stop, and you might do what I do, or what I've done in the past, and been like, uh-oh, did I make a mistake? I mean, we're looking for dy dt, which is good. We've got an x, we've got a dx dt. What about the y? So this is where, instead of panicking, you want to back up and say, okay, well, instead of y, can I replace y with something? Well, right here, I've got y equals 34 over x, right? That makes sense. We can just manipulate it. Because I've taken the derivative, remember, everything is fair game. So I'm going to rewrite this, x dy over dt plus, now instead of y, I'm going to have 34 over x dx over dt is equal to 0. And now we can start to plug everything in. So I've got my x, which is 14, my dy over dt, which is what we're looking for. So I'm just going to rewrite that, plus 34 over 14 times 1.4, and that's going to be equal to 0. Okay, so not too bad, right? Now we can keep going. So I've got 14 dy over dt plus, this is going to give me 3.4, and now 14 dy over dt would be equal to negative 3.4, and negative, which we talked about at the beginning, which is really good. So negative 3.4 over 14 is going to give us about negative 0.24, and again, meters per second, because we're looking for the height decreasing. And remember, we said a negative is a good thing because it's a decreasing height. All right, let's move on to the next one. Example number 3. A car traveling north towards an intersection at a rate of 60 kilometers per hour, while a truck is traveling east away from the intersection at a rate of 50. Find the rate of change of the distance between the car and the truck when the car is 3 kilometers south of the intersection and the truck is 4 kilometers east of the intersection. So this one, a lot of information with northeast, southwest, which some of us forget sometimes. So we've got this here just to remind us. I've got an origin, which we're just going to put right in the corner here because it's saying car is traveling north and then a car is traveling east. So north would be this way towards the intersection. East would be this way, traveling away from the intersection. So if we kind of go through this piece by piece, saying a car traveling north. So this must be the car. And it's saying at a rate of 60 kilometers per hour. So he's going 60. Now, I want you guys to think what's a positive and what's a negative. So remember what we were talking about before. If the distance to the origin is getting smaller, that's got to be a negative. If the distance from the origin is getting bigger, that's a positive. So thinking about that, that must mean that this is going to be negative 60 kilometers per hour. The truck, it's saying that it's traveling away from the intersection at a rate of 50, which if it's traveling away, that must mean it's a positive. Find the rate of change of the distance between the car and the truck. So right here, when the car is 3 kilometers south, blah, blah, blah. So let's write this all out now that we've kind of got it labeled. So our dc over dt is negative 60 kilometers per hour. dt over dt, big T over little t, would be 50 kilometers per hour, positive. What we're looking for is how far apart are they, like what is that rate looking like? So dx over dt is equal to something when, now let's go through that last little bit. When the when the car is 3 kilometers south of the intersection, so that must mean when C is equal to 3 and the truck is 4 kilometers east. So we've got a 3 and a 4 there. So it always helps just to organize your information like that because now we can set it up. So we've drawn our diagram, we've labeled everything. Now guys, we want to determine what formula to use. Now it's a triangle, so I was mentioning pretty much you're only going to be seeing Pythagorean Theorem and similar triangles. Which one makes sense here if we're talking hypotenuse? Obviously our Pythagorean Theorem, hopefully is what you're saying. So remember that's our a squared plus b squared equals c squared. In this case, we want to make it specific, so that would be c squared plus t squared is equal to x squared. Now you'll notice that we have lots of variables here, and I warned you about that in the previous lesson, that you always want to try and replace it if you can. Unfortunately, right now, there's nothing that we can replace because all of these have to be used after we take the derivative. And then we've got to play around with things just to see if we can substitute like what we've been doing in the past. So let's take that derivative. We've got 2c dc over dt plus 2t dt over dt is equal to 2x dx over dt. So what I encourage you to do is stop here and say, okay, well, what do I have and what am I missing? Well, we've got a c and a t, right? We've got c and t, we've got dc and dt, we've got dx, that's what we're looking for. What we are missing is x, little x. Now, what we need to determine is how to figure out x. Well, we actually are given enough information here. After I take the derivative, anything is fair game, which means 3 and 4 is actually the triangle that I'm going to be looking at. So if I kind of exaggerate this a little bit, let's say here, when c is equal to 3 and t is equal to 4, this is the x that we're looking for, right? Well, we can actually find the x at this given point by using Pythagorean Theorem with the 3 and the 4. Which is really cool. So I'm just going to do this in a different color. Okay, so a squared plus b squared equals c squared. I've basically got my 3 squared and my 4 squared, and that's going to be equal to my x squared. So I've got 9 plus 16. Some of you might know this already because it's one of those cool triangles. 25 is equal to x squared. So then obviously x is going to be equal to 5. Okay? Now that we know the x, we're sorted. Let's put it all in. So I've got 2 times c, which is 3. dc over dt, which is negative 60, plus 2 times t, times or 2 times t, I think I said, times 50 is equal to 2 times 5, which we just figured out, dx over dt. Now we just simply calculate. Negative 360 plus 400 is equal to 10 dx over dt. 40 is equal to 10 dx over dt. Divide by 10. So dx over dt is going to equal 4. And we're talking speed, so it's going to be kilometers per hour. Okay? Cool. All right, next one. Example number 5, or I'm sorry, example number 4 is talking about a baseball diamond. Baseball diamond is in the shape of a square, 27.4 meters on each side. Mary starts running home from third base at a rate of 2 meters per second. At the same time, Steve runs from home plate to first base at a rate of 1.5. How fast is the distance between them changing 5 seconds after they leave? All right. So here is my imaginary baseball diamond in the shape of a square. I know that that's going to be 27.4. Let's say that we make home base right here. So anybody who's played baseball before, if that's home, that would have to be 1, 2, 3, right? It kind of runs like in a diamond shape. It's saying Mary starts running home from third base. So somebody's running, or Mary is running this way, at a rate of 2 meters per second. Now I want you guys to think, is that going to be positive or negative? If she's running from third base home, is that distance getting bigger or smaller? It's getting smaller. So that's going to be negative 2. Steve, at the same time, is running from home plate to first base at a rate of 1.5. So obviously that's going away. That's going to be a positive. How fast is the distance between them changing 5 seconds after they leave? All right, so let's use Pythagorean Theorem here. Let's call that A, B, and C, because obviously we don't have similar triangles here. So let's label everything. dA over dt, we said was negative 2. We said dB over dt was equal to 1.5 meters per second, meters per second. I'm getting lazy, sorry. And we're looking for dC over dt equals how much when t equals 5. So this is the first question that we're actually given a time. So we need to figure out how we can incorporate that. Okay? So let's get started first. Write out our formula. Again, obviously we're using Pythagorean Theorem here. So we've got a squared plus b squared is equal to c squared. Okay, and we've got an a, we've got a b, and we've got a c. So I don't need to replace that with anything. All we can do now is take the, b squared. We're going to take the derivative of this. So 2a dA over dt, plus 2b dB over dt is equal to 2c dC over dt. Okay. Now let's figure out what do we have and what do we need. All right, well, we've got we've got dA over dt. We've got 1.5, and that's it. We've got a t, which doesn't fit anywhere in that equation. Okay, so we need to figure out what we're using here. Now, first of all, let's figure out after t seconds, when t is equal to 5, after 5 seconds, where is everybody? So let's use this information here. Well, if Mary, I think her name is, if she's running, yes, Mary's running home at 2 meters per second. Well, how many meters has she gone in 5 seconds? Well, obviously 2 times 5 is going to be 10, right? So A, we're going to figure out here. 2 times 5, she's gone 10 meters. So that means she's running, 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 and after 5 seconds, or yeah, I think we're talking seconds here, yes, that's going to be 10 meters. Now, this person is running this way, okay? And we're looking for the distance between them, which is this. So do I want 10 meters? Not really. I want this number right here, right? Because that's part of my new triangle, and that's a triangle we're actually trying to solve. So what do you guys think we need to do? Hopefully you're saying subtract that from 27.4, which is the whole length. So 27.4 minus the 10 is going to give us 17.4 meters. So that is our A value. Our B value, so this is our A. Our B value is along the same lines, even less work. After 5 seconds, if he's running 1.5 meters, well, obviously B is just going to be 1.5 times 5. And that's going to give us 7.5 meters. So now we've got an A and a B. With the C, we don't exactly have a speed for it yet, but remember guys, Pythagorean theorem is there for us. So let's use Pythagorean theorem in order to solve for C. So A squared plus B squared is equal to C squared. I've got 17.4 squared plus 7.5 squared is equal to C squared. You guys are more than capable of doing that yourselves. So I'm just going to give you the answer that you can check. 18.95 meters. So now we've got A, B, and C. And that now we can plug up into our equation. So let's do that. 2 times A, which is 17.4, dA over dt, which was negative 2, plus 2 times B, which is 7.5, times dB over dt, which was 1.5, 2 times 18.95, which we just found, dC over dt, which is what we're solving for. And now just calculations. This is going to become negative 69.6 plus 22.5 equals 37.9 dC over dt. Simplified, negative 47.1 is equal to 37.9 dC over dt. Obviously, we're now dividing by 37.9, so dC over dt is going to be equal to negative 1.24 meters per second. And a negative makes sense because the distance between them, okay, one is obviously running faster than the other, so that distance between them is going to be decreasing in that amount of time. Okay, so negative 1.24 meters per second is going to be your answer. All right, now guys, you're going to notice this question, example number 5. This is on your notes. However, it is an extra example, so I'm not going to do it in the podcast. I'm going to do it on another one. The reason I'm not doing it on this podcast is because you're not going to see this on your assignment or your test or your final or anything like this, but it is kind of a cool question. So if you want to take a look at it after, I'm just going to call it example number 5 on the podcast. Now, this is just simply a summary of the last little bit, or sorry, just kind of the things that we've done in the last couple of learning guides. It's saying the difference between an optimization and related rates question. So this is kind of the difference between Learning Guide 5 and Learning Guide 6. In an optimization problem, you are trying to maximize or minimize a specific quantity. So if you see the question, find the maximum sum or the minimum length of wire, etc., you know that that's an optimization question. So that's not when you're taking the derivative of everything using implicit differentiation. You're just simply using, that first derivative test and so on. Your process involves deriving both sides of an equation with respect to one variable. You are finding critical values for the function relating to quantities. So again, this is more in Learning Guide 5. In Learning Guide 6, what we did, just so you guys can tell the difference on a final exam, in related rates problem, you're trying to find out specific quantity, how it changes over time. Time is the big one. What rate is the shadow increasing? How fast is this height decreasing? So on and so on. Okay? Your process involves implicitly deriving, okay, both sides of the equation with respect to time. You are trying to find how certain measurements change with respect to time. So your radius, your height, etc., etc. So this again is just kind of a summary of what we've done in the last couple of learning guides because it is very information overload a little bit. All right, so practice some questions on this. Practice, practice, practice. If you have any questions, just go to the help desk.